Hey everyone, welcome back to more statistics. And today we're going to be looking at Skittles. So let's get to the Skittles. Mr. Ferreria loves red Skittles. But the last time he got a fun-size bag, there were no red Skittles. The bag was manufactured at the Skittles factory, where 1,000 Skittles are made each hour. 20% of the Skittles are red. To make a fun-size bag, 10 Skittles are chosen for each bag. So what are the chances of getting a fun-size bag with no red Skittles? Going down the list of bins, we can see that this is a binary setting for sure. Either you get a red Skittle or you don't get a red Skittle. But as far as independence goes, choosing one Skittle is going to change the probability that the next Skittle is going to be red. So, since the probabilities or past events is going to influence future events, we have to say that this is not an independent setting. And if it's not independent, then this is not a binomial setting. So, whoa! You thought we were going to go with the binomial setting, but it's not binomial. Number 2, find the probability of getting 0 red Skittles in a group of 10 from a factory if this is not binomial. So show your work. First thing we need to think about is, well, how many red Skittles are there? And if we have 20% of the 10,000 red Skittles, well, 20% of 10,000 is just 2,000. So there are 2,000 red Skittles to start off with, which means that there are 8,000 Skittles that are not red. And if we want to know the probability of getting not red Skittles, well, what's the probability of getting that first Skittle to be not red? So there are 8,000 Skittles that aren't red, and there are 10,000 Skittles that were made in the hour. So 8,000 out of 10,000 should be the probability of getting the first Skittle not red. Well, now that we've picked that first not red Skittles, there are now 7,999 not red Skittles out of 9,999. The probability of getting the second Skittles to be anything but red would be 7,999 divided by 9,999. And then we're going to do something similar. The probability of the third Skittle being anything but red is 7,998 divided by 9,998. And you continue that process down, that process of thinking, until you get to the very last Skittle, which would be 7,991 divided by 9,991. Okay, well now that's a probability of 10.73%. Okay, a little bit of conditional probability review for you. Never hurt anyone, of course. Our next, number 3, is find the probability of getting 0 red Skittles from a group of 10 if this was a binomial setting. Okay, so if this is a binomial setting, then we need to set up x equals a binomial setting, n equals 10, and p equals 0.8. So success in this case would be getting a Skittle that's not red. Okay, that is probability that x equals 10 now is a binomial PDF where n equals 10, p is 0.8 because we're getting 10 non-red Skittles, and of course x equals 10 because we're getting 10 non-red Skittles. And that gives us 0.1074. And just look at how similar those two numbers are. And they're even closer than you think, because actually this number was 1073.7. So we rounded it up to 1074. So they're very close. So I guess that answers part of number 4. How do they compare? Well, they're really close. Why do you think that is? And if you go back to the very first one that we did with the probabilities, I mean, 8,000 out of 10,000, that's not a whole lot different than 7,991 out of 9,991. I mean, let's compare those. So look how close that is. 80, 8,000 out of 10,000 is 0.8. And then 7,991 out of 9,991, that is 0.7998. So ridiculously close to each other. Me with my stats brain says that they're very similar because all the conditional probabilities are about the same. So 8,000 out of 10,000, that's pretty close to 7,999 out of 9,999. And that's pretty similar to 7,998 divided by 9,998. So really close. And next, to ensure that she gets more red Skittles, Mr. Ferreria buys a jumbo bag which contains 900 Skittles. So let X be the number of red Skittles in a bag of 900. Use a binomial distribution to model the situation. This is a binomial setting, or we're saying X is a binomial setting, where n equals 900 and p equals 0.2. This being a binomial setting, mu x is going to be 900 multiplied by 0.2, which is 180. And sigma x is going to be root 900 times 0.2 times 0.8, or about 12. Number 6, what's the probability of getting at most 500 red Skittles, or 150 red Skittles? Well, okay, this is a binomial CDF. So binomial CDF, n equals 900, p equals 0.2, and x equals 150. That gives me a probability of 0.0061. Pretty low. Now, if I made a histogram, what do you think the shape would be? Well, conventional wisdom, and some of the things that I was talking about before, that would be that this is going to be a right-skewed distribution. But if you think about it, and we'll go ahead and construct it for you, the peak is going to be at 180, but there's plenty of room between 0 and 180 to get the entire peak. In other words, the entire peak is probably not going to get chopped off at 0. And that's because of the large sample size. So a large sample means that we're not going to, chop off one end or the other, because the peak is going to be close enough or further away from 0 and 900, or we're not going to get any of that, clipping is what we would probably call that, any clipping. So actually, we would expect something that's single-peaked and symmetric. Since 900 is a really big number, our TI-84 can't actually handle that. But what can handle this is Staplet. And in Staplet, as we can see, look at where the peak is. It is at 180. And it is sufficiently far away from the y-axis where that is not cut off. And it's sufficiently far away from 900 where it's not cut off. So this is a lot different than, say, if we had made this 10. Now, if we make this the sample, or the size of the number of trials 10, and we plotted that, notice how the curve kind of gets cut off here on the right side. On the left side. And on the right side, it's not cut off at all. If we change that to 30 and we did the same thing again, well, no, we're not cut off anymore. We have the opportunity for this entire distribution to get that entire peak. And just for comparison, let's take a look at 15 samples. If 15 experiments, yeah, we're still kind of cut off here on the left side. And if we, of course, went to something like 50, we're going to see it doesn't get cut off on the left side anymore. So the sample size and the probability of success, they kind of work together, and if we can get that number big enough, or if we can push the center close enough to the middle, then we won't clip the end of the histogram, which means this single peak symmetric distribution is approximately normal. So look at that. What we've discovered is that we can use a normal distribution to approximate a binomial distribution, which is good for us because we have more tools for a normal distribution than we have for a binomial distribution. So let's redo the problem from number 6, and we'll do this with a normal distribution. So in a normal distribution, the first thing that I would have you do is draw the curve. Here's that normal curve that I always use. Let's mark off the mean, and the mean was 180. And then we'll kind of count off enough standard deviations until we get to, close to 150. So we can see 150 would be somewhere between a z-score of -2 and a -3. Next, we're going to shade the area. So we've marked off where we think 150 is about, and we've labeled it with a 150. And then we go to our equations. The z-score is 150 minus 180 on 12, which is -2.5. Then we write down the probability that z is less than 2.5, and we go to our calculator. Here in the calculator, we're going to go to distribution and a normal CDF. The lowest number of M&Ms that we can get is 0, and we want to go up to 150. So anywhere between 0 and 150. The mean number of M&Ms was 180 with a standard deviation of 12. We'll paste that in there, and we get 0.0062. So there is a 0.62% probability of less than 150 Skittles. Again, look at how close these two numbers are. Even if it was technically a binomial setting, we can say that we can use a normal distribution, and that makes life a lot easier, really. Well, for a lot of things that are coming up, to be honest. So let's kind of debrief a little bit here. In this first part here with questions 2, 3, and 4, these were demonstrations of what we're going to call the 10% rule. And if the sample size n is less than 10% of the population, then we can use the binomial distribution even if it's not a binomial distribution. So that's a 10% rule. We'll see that in the check your understanding parts again. And over here, we're going to get something that's kind of similar to the 10% rule. And this is a large counts rule. And if n is greater than or equal to 10, and n times 1 minus p is also greater than 10, then a binomial distribution is approximately normal. So here are those two rules. Once again, the 10% rule. A binomial setting can be approximately binomial if, when taking a random sample of size n from a population of size capital N, you can use a binomial distribution if sample size n is less than 0.1 multiplied by population size n. And then finally, the large counts condition is a binomial setting can be approximately normal if, and both of these have to be true, n times p has to be greater than or equal to 10, and n times 1 minus p must be greater than or equal to 10. Those two parts of the large count condition will ensure that the single peak distribution isn't too close to the left and it isn't too close to the right. Which brings us to checking our understanding. In a survey of 500 U.S. teenagers aged 14 to 18, the subjects were asked a variety of questions about personal finance. One question asked whether teens had a debit card. And let's say that exactly 12% of teens have a debit card, and let x be the number of teens in a random sample of 500 who have a debit card. So let's explain why the x can be modeled by a binomial distribution. Okay, well, we can use a binomial distribution even if it's not binomial by this 10% rule here. Now, the way that I like to think about the 10% rule is take the sample size, n, and you multiply it by 10. And that gives us 5,000. So now we just have to ask the question, are there more than 5,000 US teenagers between 14 and 18? And the answer is yes. Since there are more than 5,000 US teenagers, n is less than 0.1n, and we can use a binomial distribution because of the 10% rule. Number 2, use a binomial distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. First of all, I always want to write that x is binomial with a total sample with a sample size of 500 and a probability of success of 0.12. And so the probability that x is less than equal to 50 is a binomial CDF, n equals 500, p equals 0.12, and x equals 50. So that gives me 0.0932. So I'd like you to just take a minute and imagine if we didn't qualify with the 10% rule, we would have to figure out all of the conditional probabilities in order to figure this out, which you might argue is not too difficult, but in practice, that's a lot of paperwork that you would have to have done. So the binomial, the 10% rule, really helps us out in this situation. Now, for number 3, can we explain why this can be approximated by a normal distribution? So let's check out NP and n times 1 minus p, because we're going to justify the large counts condition, and we get 60 and 440. Both of those are greater than 10. So we can use a normal distribution. Now, when you're doing this on your paper, you are going to want to show the numbers substituted into the formula, and you want to show the answers here. Otherwise, it doesn't look like you're actually computing the conditions for the large counts. So make sure you write down everything. So since NP is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, we can use a normal distribution because of large counts. Now finally, we're going to use a normal distribution to estimate the probability that 50 or fewer teens in the sample have a debit card. Same idea, start off with a normal curve. We need to find the mean, and just as a pro tip for you, the mean is always located, you always calculate the mean when you do the large counts condition. So the mean is 60. The standard deviation you're going to have to actually calculate, and I've calculated that at 7.27, and 50 is to the left of 60, so we'll just start marking all of our standard deviations to the left of 60. Okay, I got to the left 52.7 and 45.5, which means that 50 is somewhere to the left of that. So I'm going to go ahead and mark that. There's 50. And we want to know less than 50, so we're going to shade to the left of that mark right there. And that's my diagram. Next, let's get our equations going. Our z-score is 50 minus 60 over 7.27, which is negative 1.376. And then the probability that a z-score is less than negative 1.376 is 0.0844. Now, I didn't go over the calculator part here for you, and I didn't go over with the equations with you. because I'm assuming that we all have that straight by now. If not, you're going to have to do some review on that, of course. Summary statement. So there's a 8.44% probability that 50 or fewer teens in the sample of 500 have a credit card. So that was our look at the mean and standard deviation again of a binomial distribution. And then more importantly, it's our look at taking a non-binomial distribution and making it binomial, or ensuring that it is approximately binomial, and then taking a binomial distribution and showing that it can be approximately normal. These skills are going to be used a lot in second semester calculus, second semester stats, and especially inference. So make sure you learn right now the 10% condition and the large counts condition. We'll see you next time, and have a good one.